Hello, this is AP Chemistry, Chapter 2, Section 8, on average atomic mass. So the natural abundance is the relative amount of each different isotope in a naturally occurring sample of a given element. Example, carbon has two naturally occurring isotopes, carbon-12, which has a natural abundance of 98.93%, and carbon-13, which has a natural abundance of 1.07%. Okay, so that's just the amount that is found of each isotope in nature. The average atomic mass is the average mass of the isotopes that compose an element weighted according to their natural abundance. So we have an equation down here that we need to explain. This is the capital sigma, which means sum. So you're adding up different parts, and what we're adding is the fraction of isotope N. Okay, and the fraction is the percentage. So we're going to write this as 0.9893 and put that down here, times the mass of that isotope. So the mass of carbon-12 is actually not 12.00. We have to look at the actual mass of the proton and the neutron, not just the rounded mass of 1 AMU, but the actual mass. So it's going to be slightly different than 12. And then we have the natural abundance of carbon-13, which is 1%, so it's going to be plus what we just said, so the carbon-12's natural abundance and mass multiplied together, plus 0.0107 times the mass of carbon-13, and we add those two values together and we will end up with the average atomic mass. Here's our example down here. Okay, our example down here is chlorine is 75.77% 35 and 24.23% 37. So to get the average atomic mass of chlorine, we're going to change this to a decimal, 0.7577, multiply it by the actual mass of carbon-35, which is 34.97 AMU, and change this percentage to a decimal, 0.2423 times the actual mass of chlorine, and you would have to look up the actual mass. This would have to be given. You can't figure that out on your own. So times 36.97 AMU, and we get 35.45, which, if you look at the periodic table, is the actual average atomic mass of chlorine. Okay, you might be thinking, how did I get the natural abundance of each element? How do we know how much of each isotope we have? We use what's called a mass spectrometer or mass spectrometry, and it's a technique that separates the particles according to their mass, and it's used to measure percent abundances of isotopes. So the spec part of spectrometry means to see or observe an image. So you guys will see the images that come out of this machine. And the ometer part means an instrument used to measure. And you can see she has her fancy mass spectrometer here, and she is being very careful not to contaminate the sample. Okay, so here's how the mass spectrometer works. We have an ionizing filament, so we need these to be ionized. We need to blast them with electrons, and they're actually going to lose electrons and become positively charged. And then we have the electron trap, the ion accelerator, so it accelerates the positive ions down this way, focusing the beam, and then the magnet is here to cause these to have to travel this curved path. Okay, and if you can picture this being like a freeway, we have motorcycles, cars, and then big semi-trucks. So who's going to be able to take this curve the tightest? The one that's going to be able to curve the most, this inner one, is going to be the smallest mass, or the motorcycle. So the motorcycle is going to be able to take the corner much faster. Okay, and then we have the car in the center, the middle mass, and we have that big truck that's going to have to make a wide turn because it's a lot harder to change. That's a physics concept. It's a lot harder to change its direction because of its greater momentum. So what we get is three different spots where we're detecting the abundance of the isotopes, of the three different isotopes in this example. and then it's going to give us the data out here. Okay, so here's an example of data from a mass spectrometer, and this is chlorine, which is Cl2. It's always in twos because this is a diatomic element. And you'll see what are the two isotopes of chlorine. It's pretty easy to tell. This is the mass to charge ratio. Okay, so the charge is usually +1, so it's basically just the mass. And this is the relative intensity on the y-axis. So there's two isotopes of chlorine. There's 35 and 37. Which has the greater abundance? 35, because it's a higher intensity. Okay, and then we look over here. These are individual atoms that when the little molecules were ionized, it must have split the atoms apart, and we have individual atoms over here. Over here, we have the Cl2 molecule. So if this has a mass of 70, which isotopes make up this peak? That's right, it would be 235 chlorine 35 atoms that make up this 70 peak. And 72 would be 2 greater, so that would be made up of, it couldn't be 2 of these, it would have to be 135 and 137. Okay, and what about this 74? That one, which is a much smaller peak, is going to be 2 chlorine 37 atoms bonded together. Okay, so this is how we tell the relative abundance of the different isotopes, and we're going to look at a few more examples here. Here's bromine. How many different isotopes does bromine have? If we look over here, the Br2 was split into the individual atoms, and we have this little group over here where we have bromine 79, bromine 80, there's a tiny amount, 81, and bromine 82. So there's 4 different isotopes of bromine represented right here. Okay, and we have 3 different peaks over here that are visible. There might be some that we can't see. And bromine 2 is going to be twice as large. So these peaks over here are from the 2 bromine atoms that are still stuck together. So what would 160 be? This 160 peak would be due to which isotopes? It could be 2 of the 80s, but chances of it having this high of an intensity is not very likely. It's going to be a 79 with an 81, making up this peak right here. Okay, and 2 less than that, what's going to be this 158? That's going to be 2 of these 79, bromine 79 isotopes put together. And then the 162 is going to be 2 of the 81 isotopes together. So these 80 and 82s are in such small amounts that we don't really see their peaks from just those 2 together, because the chances of having 2 of them bonded in one molecule would be very unlikely. Right, here's methane. I'd like you guys to think about what each peak might represent. So we have 5 atoms in this example. The last ones we only had 2 atoms. So we have 5 atoms making up all the possible combinations. Okay, so this peak is going to be just carbon by itself, carbon 12. So when it was being ionized, all of the hydrogens were lost, and we had just a carbon atom make its way through that mass spectrometer, and so we get this 12 peak. What about the 13? There's actually 2 different things this could be. If you said carbon 13, you should know that the percentage of carbon 13 to carbon 12 is about 98 or 99% carbon 12 and just 1% carbon 13. So this isn't carbon 13. This would be carbon with just 1 hydrogen bonded to it. Okay, this would be carbon with 2 hydrogens bonded. Carbon and 3 hydrogens would give us the mass, so that it's more likely that it's going to lose just 1 hydrogen when it's being ionized and form CH3+. And then this is the full CH4 molecule after it's lost its electron, become positively charged. So the greatest relative intensity is of the full molecule here, what does this peak due to? Can anybody guess? This peak would be due to carbon, and one of those hydrogens could be a deuterium, but more likely this is carbon 13 with the 4 hydrogens, 4 regular hydrogens. Okay, and I also wanted to point out that notice that these don't add up to 100%. These are not percentages. These are relative intensities. So if I wanted to know what percentage this peak was, I would have to add up all of their intensities and then take the one I'm studying. So let's say I'm looking at this one and I want to know what its percentage was. I'd have to take 100 and divide it by the total of all of their intensities added together and multiply by 100 to get the fraction. Okay, to get the percentage, which is a fraction of this guy. CO2, this is very complicated, and I'm going to let you guys think about that one and decide what peak corresponds to what part of the CO2. Okay, so this is obviously carbon. This is going to be the oxygen. What is this 22? If I had just one carbon and one oxygen, that would have a mass of 28. So that's this peak over here. What about 2 oxygens and we lost the carbon? Oh, we can't have that because carbon's in the center. So this 22 is actually a mystery to me. And what is this 29? That must be a tiny bit from the isotope carbon-13 with the 2 oxygens. This tallest peak right here is our full CO2. If you add up the C and the 2 O's, you'll get 44. What's the 45 and the 46 from? I'm going to let you guys think about that.